That means when you use an instrument to observe, to aim at a rod to get reading. So we use this blue line, blue straight line, to observe, to aim at the target. So this blue line and here right dash line, and here we have some error when you do observation. So we must take some measure to eliminate this error in observation. Okay. This some basic equipment. Next experiment, we will use this instrument to finish our first experiment, and I will send you a copy of experiment report. Okay, and then you must print yourself for each group. And after experiment, you must transfer the date you got in experiment to yourself copy of experiment report. Understand that?
Yes.
For each group, you must print one copy of experiment report. So when we do the experiment, you can use this copy to fill date you observed. After experiment, you must print again by yourself for each people, and then transfer copy the date in group report to yourself. Okay. This is basic equipment. Here is the level, and this is also level. But here is optic. This is optic. So some work must finished by your handwork. So they have many screws. For example, here we have 3 foot screws, and here have a tight screw, and here a horizontal screw, and here is vertical screw, and this is a focus screw to aim. This is a telescope to aim at the target. What target? This, the rod. Okay, the rod. And this is automatic nav, automatic horizontal lab, and here, so you can see less screen than this, because here he can accomplish the horizontal leveling automatically. So without this screw, okay, this is digital lab. The operation method is similar to this, and here also, but any instrument used for survey, there you must have 3 foot screw. For example, here we have 3 foot screw, here and then here. Okay. For this, of course, this optic has not popular. So this content in the book you can ignore. Okay. This is automatic, and this is digital. And for this difference, this can you aim at the target, and you must get a reading number by yourself. But here, this after you aim at the target, and then press the button of observation, the reading will show just on the screen directly. You just copy it from the screen to the paper. Okay. Also, you can use the memory card to record the readings. And after field work, you can download the record date to the computer, and then input to the software and process automatically. But this kind you must get the reading by yourself and do the calculate by yourself, or organize the observation date in Excel file or other format, and then input the software. Okay, and this can automatically download, and you put the software and process automatically directly. Okay, this is the main equipment. This is the rod used to get the reading. Okay, this is the theory, and this is also the most important point in this class. You must understand that. Here is point A, and here is point B. Here is point A, and here is point B. So, if we want to survey elevation difference between point A and point B, firstly, we say, if you survey from point A to point B, then we say we have two directions. From point A to point B, we do the survey. So this direction is forward. So this direction, we call it as backward. So from A to B, so this is forward and this is backward. Okay, backward. We must have direction in the elevation difference, because the elevation difference between point A and point B have direction, have plus or minus. So we must tell the difference of the direction of leveling. So from point A to point B, so this is forward and that is backward. Then we place the level just at the center of these 2 points, roughly. Here we place the instrument of level, and then place two rulers on point A and on point B. This is leveling rule. This also leveling rule. Of course, because we have direction, so we call this rod is forward, and this is back rod. Back rod. Then we use the telescope to aim at the rod and get reading. Firstly, which direction, which rod we should aim at? Firstly, forward? No. Firstly, we must aim at the backside, backward. Here, aim at the back rod and get reading. So we get a reading A. The A is just the distance from the site position to the point. Yeah, it's just this distance. Yes. Then turn around, rotate the telescope. The telescope can rotate. Then aim at the forward side, okay, and get the reading B. The reading B. So the elevation difference equal what? Equal A minus B. I think in this rectangular shape, I think the elevation difference is just like this, because this is the geoid. Of course, we say the geoid is a curvature, yeah? But in this small area, this very small distance, we can think of the geoid as a straight line. Okay, so in this rectangular shape, we say because this line parallel to this and be parallel to the line of sight. So here is the elevation difference, because this is point B, this is A. So the elevation difference is just this distance, yeah? Okay, HAB plus B just equal A. So A minus B just equal elevation difference between point A, B. Okay, we have something important here. Why we must aim at the back side, then foresight? So because here we have direction, so HAB always equal backside reading, A minus foresight reading. Okay, this is HAB. If you want to get the elevation difference between B and A, that means survey from point B to point A. That means the elevation difference will written like this: HBA will equal what? Equal what? B minus A. So, because the elevation difference will have direction, if the result is plus, sometimes the result may be minus, yeah? If the plus, that means we go up. If the elevation difference is minus, that means we're going down, yeah? Going down. So, have difference. So, the elevation difference have direction. So, we must distinguish the forward or backward. So, for forward, we say the reading is foresight reading. The backward is backside reading. Okay, here, if we get the elevation difference between point A and point B, so in this situation, if point A we have no its elevation, so the elevation of point B we can calculate. So use the elevation of point A, HA, plus elevation difference HAB. So we can get the elevation of point B. Okay? Of course, this is very, very simple. But sometimes we do some change like this. This is one method we can calculate the point B. Another method is like this. Of course, HB equal HA plus HAB. Of course, we will equal HA plus backside reading firstly, then minus foresight reading. Yeah? Of course, because HAB just equal A minus B. Yeah? Here, we just change the compute order. Yeah? The result will no difference. But this formula just means different observation method. Why? Like this. If we say HB equal HA plus HAB, that means we have one backside point and one foresight point, and the backside point, the elevation is given. Then we place the instrument and get a reading A, get a reading B, and then determine the elevation of foresight points. Yeah? This method, this formula. But for this formula, we have a difference. Why? Because this formula is just a suit 2 points, one backside point and one foresight point. And this formula will use for many foresight points. For example, in some special situation, we have a backside point A, the elevation is given, and we have many foresight points in engineering project work. In this situation, if you use this formula to calculate the foresight point elevation, you should repeat this observation many times, But use this formula, you can place the level instrument only 1/10, and then get the backside reading still is 8, and then place the forward rod many times. For each point, you can get a forward reading, B1, B2, B3, B4. Yeah? So for each point, we just use the same backside reading. Yeah? So when you do calculation, here for each HB, you are equal HA, the backside point elevation, plus backside reading A, firstly, and then minus each forward reading BI. Then we can get elevation of each point. Yeah. So in this situation, we just place the instrument only one time. But if you use this formula, you must place the instrument here many times, many backside reading. Yeah. So in fact, the result over here, elevation of back points plus the reading of backside, we just get the height of what? The height of the site. The height of the site. Okay? This is two different methods in observation, elevation difference. Although elevation difference. Okay. This is the theory of lab. Here, the instrument should be placed at the center of these 2 points, roughly. Of course, why we do that like this? We should place the instrument at the center, at the equal distance between these 2 points, roughly. Why? Because we said before, the geoid, in fact, is not a straight line. Sometimes, no, sometimes. In fact, it's a curvature, yeah, curvature line. But the side is a straight line. So a straight line, in theory, we want to use this straight line to parallel to the geoid, yeah. But in fact, it's not. That means because the error of reading. So if we place the instrument at the center, at the equal distance between these 2 points, roughly, that means the error caused by forward reading and caused by backside reading may be equal roughly. Yeah? Maybe equal roughly. So the error caused by forward reading and backside is equal roughly. In this formula, you can see HAB will equal what? Will equal A minus B. That means the error caused by A and the error caused by B will be eliminated. Yeah? Eliminate. So let's say here, if we use this blue side to take place the right dash line. So when you place a rod, backside rod here, and forward rod here, so when you take a reading, this distance may be caused by reading precision. So this is forward reading error. This is backside reading error. Yeah. If the instrument have the same distance, equal distance here and here, so the error should just be equal roughly.